All right, guys, welcome to our lesson on limiting reactants. This should be a topic that you're at least familiar with. Start with how many cookies could I make? You guys, so look at the ingredients. You guys ever made any cookies? You need some butter, sugar, flour, eggs. Is that milk, I assume? Looks like a full thing of milk. And you think about it, it says you can continue to make cookies until what? You just keep making cookies until what? At some point, you're going to stop making cookies when? When you're tired? Well, maybe. Isn't it? And you guys, the answer is it's not when you run out of all the ingredients. No. You can keep making cookies until you run out of even one ingredient. And if you guys look, I don't know if you guys can see it well, which one does it look like you're going to run out of first? You guys, like there's just a little bit of sugar. You ever had cookies without sugar? It tastes pretty nasty. Once you run out of sugar, you're going to be that's going to limit how many cookies you can make, and therefore we call sugar. What will we call sugar? I'm going to try to speak up. I think the audio on this is not too well. We call sugar the limiting reactant. Okay, so it's like a limiting reactant, right? That would be the we'll move on and we'll see. Okay, so the limiting reactant is the reactant present in the smallest stoichiometric amount. That sounds really big, right? In other words, it's the reactant you're going to run out of first. So look at this. You can have a reaction with hydrogen and oxygen. You guys know hydrogen and oxygen can combine in a combustion reaction, an explosive reaction, producing, you guys see the little Mickey Mouse molecules. You guys should know that's water, right? One oxygen, two hydrogen. So in this case, we have a bunch of oxygen and hydrogen, and then what you can do is you just can ignite it. Oftentimes we need heat to initiate the reaction. You can see they come together, form water, and you guys see what's left over. We have oxygen molecules left over. And what don't we have any more of? Hydrogen. So what do we call hydrogen? Hydrogen is the limiting reactant. Because even though we still have oxygen left over, if there's no more hydrogen present to react with, that is just going to be left over. Okay. And so in this case, oxygen would be called the excess reagent, or the reactant in excess. Excess meaning we have more than we need after the reaction. Okay, so you guys, we're going to do several calculations today. Here's a typical stoichiometric calculation. So we have, you guys, this is a reaction you guys should be very familiar with. It's perhaps the most important, or one of two of the most important reactions to life. And you guys, I'm hoping you guys don't say it's photosynthesis. Remember, it's the opposite of photosynthesis. In this case, you have glucose reacts with oxygen to form carbon dioxide and water. You guys, that's cellular respiration. That's what's happening in all of our cells. That's why we're able to function. Because this is an exothermic reaction, energy is released, our body's able to store the energy given off in this reaction. So what do we take in? Yep, we have to eat. So we eat, primarily our energy source are going to be sugars, glucose. What else do we take in? Oxygen. Cellular respiration undergoes in our mitochondria. And what is the byproducts of this reaction? You can see it's just a rearrangement of atoms. The atoms we start with are the atoms we end with. And we end up with carbon dioxide. And not only carbon dioxide, we often know, but if I were to blow on a glass, it's going to get all foggy. That indicates what else is coming out is water vapor. Okay, so here's the question I have first is how much water, we're going to start with one question. How much water can be produced when 10 grams, wait, did I already do, I think I missed, oh, you know what, oh, okay, that's fine. Okay, sorry guys. How much water can be produced when 10 grams of glucose undergoes cellular respiration? Okay, so you guys, what we're going to do is, here's a little map. In fact, I would copy this down. Some of you guys might already be able to follow it just kind of by memory, but we can follow a map. It says how much water can be produced when 10 grams of glucose undergoes cellular respiration. What I've always encouraged people to do is take the information you're given in your problem and then put it by the corresponding substance in your chemical equation. You guys will notice, remember, you always have to start with a what kind of equation. Whenever you're doing a calculation, it's always got to be a balanced equation. So realize this has already been balanced. You guys see the coefficients have already been placed. I'm trusting that you know how to balance chemical equations. If not, you guys talk to me and we'll go over a few to make sure you guys know how to balance, okay? So, question is how much water can be produced when 10 grams of glucose undergoes cellular respiration? So what I would do is I'd take information from here and put it over the corresponding substance. It tells me I have 10 grams of glucose. I find my glucose, I have 10 grams. Okay, and then the question I'm asking is how much water can be produced? So I'm going to water, that's my question, I don't know. And it says how much, in this case we'll just do grams. Okay, So the question is, how do I figure out how much water I can produce here if 10 grams of glucose reacts? The key is you use what a little roadmap that I've developed, okay? So if you guys look, so A is the substance that we know information about, and B is the one that we don't know information about. So glucose is like our A, and what do I know? I've got 10 grams of it. So I know the weight of A. So I'm gonna go from here, okay? And then what do I wanna figure out? I wanna figure out the weight or the gram or the amount of B. So I'm gonna go here. And so I'm looking and look, so I'm gonna first convert to moles. When in doubt, convert to moles. Then I have to go from moles of A to moles of B. And then I go from moles of B to weight of B. So this is like a roadmap, and what this tells me is I'm gonna take 3 roads. So that's what I'm gonna proceed to do. I'm gonna put it right here. So I'm starting with 10 grams of glucose. And I ultimately wanna figure out how many grams of water I'm gonna produce, okay? So, first thing I gotta do is convert weight of A to moles of A. So in order to do that, you guys should remember, you use your periodic table, you add up all the individual atomic weights of all the atoms that make up that compound, and that will give you the molar mass. I think I wrote it down. It's 180, so if I add up all these, remember carbon weighs 12, hydrogen 1, and oxygen 16, and then I got 6 of those and 6 of those. It's 180 grams per mole. So I got 180 grams of glucose is equivalent to 1 mole of glucose. And it might seem kind of tedious to write down the molecule, but because we're dealing with 2 different substances, you want to write down, otherwise you're going to get confused. So look, grams of glucose cancels out. So at this point now I'm at moles of A, okay? I need to get to moles of B. You guys remember what links the 2 different substances is the mole ratio. We use the mole ratio right here. And that's where I look to my chemical equation. Hopefully this is a review for a lot of you guys. You guys I look at the coefficients. I compare coefficients. One of these reacts with 6 of these to produce 6 of these and 6 of those. So one of these will produce 6 of these. These are the 2 things I'm interested in. You guys see, that's the nice thing about writing it initially. I'm only focused on these 2 things for this particular problem. So it's a 1:6 ratio. So what I would say is 1 mole of glucose, C6H12O6, essentially will produce 6 moles of water. And then moles of glucose cancel out. Now the last thing I got to do is go from moles of water to grams of water. See, moles of B to weight of B. And you guys remember how you do that? It's always the molar mass. Molar mass of water is 18. You should know hydrogen is 1, but I have 2 of them. So that's 2, and then oxygen weighs 16. That's 18 grams per mole. Well, I got the mole on top, so I'm going to put the 1 mole of water on the bottom, and that's equivalent to 18 grams of water on the top. Okay, so then you guys remember what you do. You multiply all the top, 10 times 6 times 18, and then I divide it by 180, and what I'm going to get is 6 grams of water. So if 10 grams of glucose reacted, let's say I consumed 10 grams and it was perfectly efficient, what am I going to be breathing out? 6 grams of water. Okay, moving on. Number 2, you guys remember this is the whole lesson is kind of about limiting reactants. What is the limiting reactant when 10 grams of glucose reacts with 5 grams of oxygen? Okay, so it's a different problem. Remember what I said we do? In our problem, we take any information in the problem itself and we put it over the corresponding species in the chemical equation. So we've got 10 grams of glucose again, and we've got 5 grams of oxygen. And you guys see why we have to figure out the limiting reactant, because one of them I could have more than enough, and wouldn't you guys agree, one of these might run out before the other, and the reason why it's called limiting reactant, because once that runs out, that's going to limit how much products you produce. So here's how you determine, we want to know which one runs out first. And I know you guys, the thing you do not want to do is, you don't want to say, oh, oxygens are a limiting reactant. And I can see where somebody said it, because, well, we got less of it than that. But you guys remember, you can't compare masses, you got to compare numbers of molecules. So we always need to ultimately convert to moles. So here's how you do it, to figure out what is the limiting reactant. You just start with one, and you just figure out how much of the other one you might need, okay? So for example, you could start with 5 grams of oxygen, or you could start with 10 grams of glucose. I'm just gonna start with 10 grams of glucose. So here's what I'm gonna do. I'm gonna say I've got 10 grams of glucose, right? And this time, rather than figuring out how much water I would produce, I'm going to figure out how much oxygen I need. So I'm going to use the same, route, okay? Okay, but I'm doing it with these two now, okay? So I'm just focusing on those two. So once again, let's say you don't even have this roadmap written down and you're like, man, I forgot what to do. You guys, what do we say? When in doubt, you're going to convert to moles. Always convert to moles, guys. So I'm going to convert this to moles, so it's the same thing, 180 grams. You guys see just like we did before, okay? Okay, so then I cancel out grams. So now I got moles of glucose. And you guys remember, how do you link two substances? You always use what's called the mole ratio. Once again, these are the two things we're interested in now. Remember, it's always two things you're just focusing on at a time. And you guys, what's the mole ratio between these? One of these reacts with 6 of those. You guys see that? It's a 1:6 ratio. Glucose on top, so I'm going to put my 1 mole of glucose on the bottom. And I'm going to put the 6 moles of oxygen on top. So it's a 1:6 ratio. And you guys see the last thing I got to do is I want to convert it. I'm sorry, I probably should have put it over here. I want to see how much. I don't know if you guys can see that. Grams of oxygen. Hopefully you guys can see that. Grams of oxygen. Okay. So I need to go from moles to grams. Once again, that's using the molar mass. Oxygen, you guys remember, weighs 16. But you guys remember, look, you got to be careful. It's diatomic. It's O2. There's 2 oxygen atoms. So it's not 16 grams per mole. It's 32 grams per mole. You multiply it by 2. So it's 1 mole of oxygen weighs 32 grams. So then I multiply the top, divide the bottom, and what I'm going to get is 10.7. Here, let me see if you guys can see it. Yeah. So you guys can see it. 10.7 grams of oxygen. So now I want you guys to look, maybe pause it and go and try to think, okay, based on this information, what's my limiting reactant? Does glucose run out first or does oxygen run out first? Okay, pause it, think about it. Okay, here's what you guys you need to know. This is 10.7 grams of oxygen is needed to fully react with all of my glucose. So what do? I compare what I need to what I have. This is what I have. So if I need 10.7 grams to fully react with all my glucose, but I only have 5 grams of glucose, what does that indicate? What's going to run out first? So for all my glucose to be used up, I would need 10.7 grams of oxygen. But I only have 5 grams. What's going to happen, guys? The oxygen is going to run out first. Right? Because once the 5 grams, and what's going to happen is I'm going to still have some glucose left over. So the reality is, guys, that is my limiting reactant. Okay. So, moving on. Guys, one last concept. Hopefully you guys picked that up. How once again you just start, and you could have started with 5 grams of oxygen and figure out how much glucose, and then did the same kind of comparison, and you ultimately come to the same result that the oxygen is going to run out first. Okay. Here, let me see the time. Okay, I think we're doing all right on time. Here, let's say a video. Maybe hearing it from a different perspective, you might better understand it.
Nitric oxide, NO, is produced when atmospheric nitrogen and oxygen react at high temperatures in an automobile engine. Once released into the atmosphere, nitric oxide is quickly oxidized to nitrogen dioxide, NO2. Nitrogen dioxide is a toxic brown gas. Much of the brown haze present in photochemical smog is due to the presence of nitrogen dioxide. The left side of the two-bulb vessel contains nitric oxide gas, NO, and the right side contains oxygen gas, O2. Click on one of the buttons to choose the number of molecules of NO you would like to react with the number of molecules of O2.
Okay, so you guys, what they're going to do is, what they're saying is, we have, I think, nitrogen oxide here in the left side, and then oxygen in the other, right? And then those two will react and form NO2. So what we're going to do is open up the valve, and so I'm going to do a scenario where we have equal amounts of nitrogen oxide and oxygen, and we'll see what happens.
Nitric oxide and oxygen gas are reacted in a 1-to-1 mole ratio. There are 4 molecules of NO.
4 NOs and 4
and
0
4 molecules of O2 in the right bulb. The valve separating the bulbs is open, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 4 molecules of NO are reacting with 4 molecules of O2. The 4 NO molecules require only 2 O2 molecules for reaction. Note the 2-to-1 mole ratio in the balanced equation.
It's a 2-to-1 ratio.
Therefore, 2 O2 molecules remain after reaction.
So hopefully,
the
guys.
reaction stops once the nitric oxide gas runs out. NO limits the amount of product that can be formed and is therefore called the limiting reagent. Oxygen gas is present in excess.
So hopefully you guys can realize that NO is the limiting reactant, right? Because you don't see any more, and oxygen is the one in excess. And you guys should have predicted that because you guys look at the mole ratio. For every 1 oxygen that reacts, I need twice as much NO. But when we added it, we added the equal amount. So therefore, we did not add enough NO to fully react with all of the oxygen, and that explains why oxygen is still left over. Okay, guys, last concept. Well, first, could you freshen my drink, Sal? Flush. Okay, you guys know dogs like drinking out of the toilet, okay? Okay, guys, last concept. The theoretical yield is the maximum amount of product. You guys, that's in purple, so that's why I'm saying is really important. Theoretical yield, the maximum amount of product that can be produced. It's the amount of product that is possible from a chemical reaction. Now that's different. The theoretical yield is different from the actual yield. Actual yield is actually how much you actually recovered as opposed to how much you theoretically expected to recover, okay? One finds the percent yield by comparing the amount actually obtained to the amount that was possible. So you guys write this down. This is in purple. I don't know if you guys can tell the color. Percent yield is the actual yield. That's what we actually got over what we expected, or otherwise known as the theoretical yield, and then you multiply it by 100. Okay, we're going to apply that. Last question for today. Let's say we had 2 grams of water was collected in a reaction with the condition stated in question number 2. So you guys remember in question number 2, we had 10 grams of this and 5 grams of this. And what we want to know is, we actually ended up collecting 2 grams of water here, okay? We want to know what the percent yield is. So here's how I would solve this. I would go, okay, percent yield, you guys remember, is the actual over the theoretical times 100. Well, this is what I want to know. What do I already know? It tells me I've got 2 grams I actually collected. That's right here. So the only way I can calculate this is if I know the theoretical yield. So that's ultimately what I'm going to try to figure out. How much of that can I theoretically produce? So here's where there's a dilemma, guys. If you're given multiple reactants, do you guys remember what do you guys need to do first in order to determine how much product you're going to form? You first have to decide which one, once again, is the limiting reactant. Because you guys remember, once that's used up, that limits how much of the product's produced. So you guys, we already did that. You guys remember which one's the limiting reactant? You guys remember we figured out from problem number 2? This is the limiting reactant. So what that means is I'm going to use this amount to determine how much of that. I'm not going to use 10 grams of glucose. Why not? Because not all 10 grams was able to react. Remember that? Because it's going to stop once all the 5 grams of oxygen. You always start with the limiting reactant because that ultimately determines how much product. So that's what I'm going to use right here. So I start with 5 grams of oxygen, and ultimately I want to see how much grams of water I'm going to produce. So I'm going to go kind of quick here, guys. When in doubt, convert to moles. It's 32 grams of oxygen is 1 mole of oxygen. Okay, and then you guys remember how I go from oxygen to water. I use the mole ratio. You guys see what the mole ratio is this time? It's a 6:6. It's 6 moles of oxygen for every 6 moles of water. It's a 6:6 or 1:1 ratio. And moles of oxygen cancel. And then lastly, I just got to convert from moles to grams. And you guys remember, I put the mole on the bottom. And you remember the weight of water, the molar mass of water is 18 grams per mole. And then you guys, like the 6's can cancel, so I don't have to do that. I go 5 times 18 divided by 32, and what I'm going to get is 2.8 grams. So that is theoretically how much water I should have produced from this reaction, but in actuality, how much did I collect? 2 grams. You guys usually, when you're doing a lab, you're never going to get 100% collection, right? Because there's always experimental error, right? So the question is, what's my percent yield? So you guys remember what you do is, I compare my actual, which was 2 grams, and I divide that by my theoretical, which was 2.8 grams. So I go 2 divided, sorry, this is a mess, guys. Maybe if I did it in a different pen, you guys can see it. 2 grams was my actual. I'm going to divide that by 2.8, which was my theoretical. I do that, and I'm going to get 0.71 multiplied by 100%, and it's 71%. So I collected 71% of the amount of water that I theoretically expected to produce with those conditions. All right, guys, I think that is it.